Cl2. Remember the diatomic stuff? I bring clay for our new house, and you all know what that means, right? Okay. This is diatomic. But we know they go together. And they're going to go together and make chlorine, Cl2. Okay, let's look at this. How many valence? Eddie, how many valence electrons does a chlorine have?
7.
7. I'm going to draw it this way. Okay, I've got 7 around this guy, and I've got 7 around this guy. This guy wants to gain 1. This guy wants to gain 1. It is not a good setup for ionic at all. However, could you visualize them scooting together and sharing that pair? Okay, this works so well because with a bond like this, they're sharing, and the definition of covalent over here is a sharing of electrons. Sharing of electrons. Okay, the beauty of this is, if I cover up this guy, this one feels like it has access to 8, the octet. 2, 4, 6, 8. It feels like it's isoelectronic with argon. If I cover up this guy, he feels like he has 8. 2, 4, 6, 8. I wish bank accounts worked that way. Okay, so here everybody feels like they got the full complement of 8 by sharing. So this is referred to as a covalent bond. After you do a few of these and you go nuts counting electrons and putting dots, here's an alternative. Usually we move from here to here, where a straight line represents 2 electrons, and this represents the 2 that are shared. So these are referred to as bonding electrons, and all the rest of these guys are referred to as non-bonding electrons. So that's what the covalent is, a sharing. Now, let's move into section 5, the very most important section, and then I'm going to come back to 4, because in my opinion, they put it in the wrong place. So, most important thing, how important is it? If you cannot do Lewis dot structures for compounds, you got to blow off the rest of chapter 7 and all of chapter 8. If you don't develop this skill this morning or really soon, you can't do anything else in chapter 7 or 8. That's how important it is. Years ago, my students used to have to do Lewis dot structures by trial and error. It was possible, but it took them lots and lots of time. Our textbook, and I first saw this equation in this textbook in a previous edition. These authors were the first that used it that I was ever aware of. This equation. And let me define each of the terms. First of all, here, S stands for number of electrons shared. Okay, so right off the bat, this equation is only for covalent stuff, because this is number shared. This is total of electrons needed. And I want to stress total, because I'm changing the language on you a little bit. You know, before, when we looked at chlorine, you would tell me it needs 1 more. Okay, now, N here stands for total need, and the total need of most of these will be 8. It's total need. Chlorine needs to have 8 in its outermost shell, so the need is 8. So you don't answer that question, how many more does it need to pick up? You give the total. And then here, number of electrons available. And this means valence electrons. Okay, two things about that equation. You've heard one, and here's the other one coming. First, it is only for covalent stuff. Second, the equation is only for the valence shell electrons. We don't care about what's buried underneath. We only care about the outermost shell. Now, I'm going to take a whole bunch of these this morning, and they're going to get progressively harder. So if you see one that's problematic, slow me down. That's your responsibility. So let's go back.
So a question on the test would just be like, how many number of shared electrons?
That could be, yeah, that could be. But also, which is the correct Lewis dot structure for this substance? That kind of stuff. So here's the skill we need to develop. I give you a formula, and I will say, write the Lewis dot structure for this. Now, we did that just a moment ago. We did it here by the old trial and error system, saying, hey, I bet if they scooted together and shared one pair, they'd both be happy. Well, chlorine is a pretty simple case. And we're going to have more complex molecules where the ideas won't come that quickly. So we're going to go through this, first for chlorine. Okay, so I want to solve for chlorine. N and A and finally S. Okay, I have two chlorines. Each need 8. Now I'm going to do this first one, and then you're going to start helping me on the next one. They each need 8, so the total need is 16. Okay, now, how many valence electrons does a chlorine have? Anybody? 7. Each one has 7. So we have 14 are available. How many are they going to share?
2.
2, the difference. So, here's how we build them. I put a chlorine and a chlorine side by side. It does not matter if I put them left, right, up, down. Orientation doesn't really matter here, because when we do Lewis dot structures, it doesn't show you molecular shape. It is bookkeeping. In Chapter 8, we're going to take Lewis dot structures and move on with them and get actual shape of molecules in 3-dimensional space. That's what we're gearing up for. So, it says share 2. So I put 2 in between them. And then I say, okay, this guy has 2 right now. How many more electrons does he need to be happy? And you would say what?
6.
Well, 6 for this guy. Okay, then I would look at this guy, and I would think, how many it feels like it has right now. Hina, how many more dots does this guy need? 6. And we get to this point. There's no reason to miss these because we have ways to go back and check our work. Okay, did we share 2? Yes. Okay. Did you use 14? A check of this and a check of that are so important because we got to use 14. No more, no less. So we come over here, and did I use 14? 2, 4, 6, 8, 10, 12, 14. Check, and we use the 2 to share. Okay, now this business about need. If you try to count 16 electrons, you're not going to find them, because that is the duplicate there in the middle. So here's how you check to be sure. Your last thing to check. Cover one of them up and say, does it have 8? Yeah. Cover this one up and say, does this one have 8? Yeah. So this would be our finished product. And then when you start going nuts, doing all these dots, you're going to do that. And remember, these are called the bonding electrons. And when you just share 2, this is referred to as a single bond. A single bond. Now, some books will say single covalent bond, but that's redundant. Because if you say a single bond, that will always refer to a covalent bond. It will never refer to an ionic bond. You just don't use that language with the ionic substances. Okay, now, let's do another one. if I have oxygen, if I bought a tank of oxygen, okay, or in the hospital where they're using oxygen tanks, monatomic or diatomic? Diatomic. Okay? So let's draw the Lewis-Dot structure for oxygen. And again, trial and error would work, but this formula works better and faster. So let's go. N, A, and share. Okay. An oxygen needs how many total? Meredith, what would you tell me? 8. Now, would you allow me to collect terms? Instead of saying 8 plus 8, I'm just going to say I've got 2 and they each need 8, so the need here is 16. Okay, now, each oxygen comes in with how many, Antonio? How many valence electrons does an oxygen have? Oxygen? Look at the family name. It's a wonderful clue. It needs 8, but how many does it have right now? 6. Your friends are saying 6. Do you buy that? Yeah, you better. Okay? Okay, let's think about it. And okay, I don't want to put you on the spot, Antonio, but if you have an issue, there's probably other people who have the issue. You look up here. And my question for you was, how many valence electrons does this have? So let's think electron configuration. It would have a helium core, and then we'd say 2s2, 2p4. 2 over there, 4 over here, 6 valence. Because valence is major outermost. Okay, so let's come back here. Each one brings to the table 6. Allison, how many are we going to share? How many are we going to share? Look at this.
4.
So how many will we share here? 4. Okay, now let's come over here. I put the O and the O side by side. And again, if you want to put them on top of each other, I don't care. And we're going to share 4. Now, I'm just going to do it that way, because I'm tired of doing dots. So 2 dots here, 2 dots here. Okay? Now, each of them feels like they have access to 4 already. So let's come over here. How many more electrons should I put on this oxygen, Bruce?
6.
6 more?
You got 4, you
You
got
got
8. Only 4, I'm sorry.
4 more.
Yeah.
Okay, now, does it matter where I put the lines? I can put it top and bottom, I don't care, side and bottom, that's not important at all. Bookkeeping is what counts. Okay, this guy over here, Marco, how many more?
4.
4, or 2 lines. Now be very careful with the language. People in the past have had trouble with the language on the review sheets and the test. The question sometimes is, how many more pairs of electrons does it need? And each one would have needed 2 pairs. Or sometimes the question is, how many electrons does it need? And you say 4. If you will think of your shoes, okay? I am wearing 1 pair of shoes, but I'm wearing 2 shoes. Or in your closet, and everybody's looking at my feet, okay? Yeah, sandals, I will change for lab, okay? All right, in your closet, let's say you have 10 pairs of shoes. Then you got how many shoes are sitting in your closet? 20. Okay, think of electrons the same way, so watch the language. Are they talking about how many pairs, or are they talking about how many electrons? Because the answer will be different. When you have this sort of thing, they call that a single bond. Take a wild guess what they call that, a double bond. And sometimes you hear people say double covalent bond, but again, that's redundant. Singles and doubles only refer to covalent. Okay, let's do another one. The nitrogen here in this air, and about 80% of what we're breathing in is nitrogen. Monatomic or diatomic? Diatomic, okay? let's run through this process. Okay, we talk about need, we talk about available, and we're going to talk about share. Notice something just horrid about chemists. N here stands for nitrogen. N here stands for need. N in chapter 4 stood for major energy level in the quantum numbers. It's because there's only 26 letters in our alphabet. And so they get some double and triple usage. So you've got to look at context. You know, if I just step in the room and go, what's in? That's not a valid question. I say, elements, what's in? And then you say, nitrogen. Up here, I pointed this one, and you know I mean need. Each nitrogen needs how many, Nina?
Oh, 2.
No.
Oh, wait.
Think music.
Oh, 8.
8. If your back's against the wall on need, 8 is a real good guess. Okay? All right. Now, available. We have 2 of them. Pedro, how many does each nitrogen come with? 5. So we have a need of 16, and we only have 10 available. So we're going to share how many, Emily? 6. Yeah. So we come over here, and 2, 4, 6 are shared. Take a wild guess what they're going to call that. Think baseball. A triple. And we do not go any higher than triples. But let's go back and finish this off. Think about, if I cover this guy, how many does this feel like it has right now, and how many more, Brittany, do I need to put on here?
1.
1 pair or 1 electron?
1 pair.
1 pair. This guy over here then, Nicole, how many more?
1 pair.
1 pair. And see, you all have to be careful now when you answer me. 1 pair or 1 electron. You ought to say which it is you're talking about. Okay, so we have a single, a double, and a triple bond. These could be done by trial and error, but it becomes problematic because if you're doing trial and error, and some of my students do because they're too stubborn to do this, fine, have at it. But like with oxygen, you put an oxygen here and you put an oxygen here, and you try a single bond. Okay? It's not going to work because everybody can't get an octet with oxygen, oxygen, and a single bond only. So you then try a double. Well, hey, that worked. But then think about nitrogen. First you try a single, doesn't cut it. You try a double, doesn't cut it. Then you got to try a triple. That cuts it. So think how this will streamline doing this. Okay.